In today's video, we will be discussing how selection can alter genotypic and allele frequencies in a population. The key to understanding the effect of selection is the Harvey-Weinberg equilibrium principle. HWE is the principle that allele frequencies will stay in equilibrium unless one or more assumptions are violated. To be in HWE, a population must be infinitely large, randomly mating, not experiencing any emigration or immigration, must not be under selection, and there must be no spontaneous mutations. To demonstrate HWE and the effect of selection, we will be using a fictional animal called Ursus gelata, which is an animate version of gummy bears. Gummy bear pigmentation is controlled by one gene with 2 alleles and is stratified into 3 phenotypes, as can be seen on screen. Our population is 60 bears. We must use chi-square analysis to test our hypothesis, which is that the population is in HWE. We have 31 pineapple, 23 lemon, and 6 orange bears, and from this we can derive that the frequency of big A is 70% and that of little a is 30%. Next, we can use the Harvey-Weinberg equilibrium formula, which is p squared plus 2pq plus q squared, to figure out the expected genotypic ratios. And we can see that the expected ratios are quite different from our observed ratios. The table on screen shows the inputs used to calculate the chi-square value, which in this case is 0.346. Since this value is below the relevant critical value of 3.84, we will fail to reject the hypothesis and can say that the gummy bear population is in Harvey-Weinberg equilibrium. Next, we will use an example to examine the effects of selection. The primary natural predator of the gummy bear species is the sticky-fingered small child, formerly known as Homo littleboyensis. Little Boy greatly prefers to eat lemon gummy bears, with pineapple ones being a second favorite, but he doesn't like orange gummy bears at all. On screen now is the table we will use to calculate the new genotype frequencies after selection. We first must multiply the initial frequency of each genotype by their respective fitness. The resulting number is the unadjusted frequency after selection. The problem is that the sum of the frequencies in this row does not equal 1, so these are not actual real percentages. To normalize them to 1, we divide each frequency by the sum of the row, which is the average fitness, which is 0.587. This gives us the adjusted numbers. By multiplying the total population by the average fitness, we can get the expected number of individuals after selection, which is 35.22. As you can see, the number of lemon bears drops off a cliff, while the number of expected pineapple drops only slightly and the orange bear stays steady. This is an example of disruptive selection, as the extremes of the distribution are favored over the middle, and if selection continues, the homozygous genotypes will become more common and Homo littleboyensis will probably get a bad sugar crash. Here are my sources.